We are dealing with the knowledge area chemical change. Let's look at the Avogadro's number. Right? Let's look at the Avogadro's number. Sometimes I also refer to it as the Avogadro's constant. Now the Avogadro's constant is one of the 7 natural constants. The SI base units are now linked to natural constants and no more to physical prototypes. The mole is linked to the Avogadro's constant. The Avogadro's constant, as you may now know, is defined by a fixed numerical value which is exact. We, however, will use the approximate value in our calculations. Right, and the approximate value is 6.02 times 10 to the 23. Now the Avogadro's number, right, is used to convert between the chemical amount and the number of atoms, ions, or molecules, right? It converts from the chemical amount to the number of elementary entities. So if you look at it here, N, capital N, is the number of elementary particles. Small n is equal to the amount of substance, and see what its unit is. Its unit is mole. Na, which is the Avogadro's constant, is that, and its unit is mole per mole, right? Mole, right, which is the same as 1 upon mole, right? Per mole, something per mole. What per mole? Right? It could be atoms per mole. It could be ions per mole. It could be molecules per mole. Or it could be electrons per mole. Or any other entity that we want per mole. Right? So, a mole is actually a unit of quantity. Right, and I have mentioned in the previous video, it's a counting number. But what we actually do is we mass the substance, we get the mass of the substance, and by getting the mass of the substance, we are essentially counting the amount of particles in a mole of that substance. And a mole is 6.02 times 10 to the 23 things. What are these things? Like I've mentioned earlier, it could be atoms, ions, molecules, right, or any other entity. If we look at here, we've got the number of atoms, molecules, or other fundamental units. And on this side, we got the number of moles. So if we want to go from the number of entities to the number of moles, we must then divide by 6.02 times 10 to the 23. If we're moving from moles to elementary particles, we multiply by 6.02 times 10 to the 23. Right, now we're going to apply this to some of our questions. So let's look at the first one. We want to know the number of molecules of that in 0.35 moles of C6H12O6. Okay. Now, we know that N is equal to small n times the Avogadro's constant. But how many moles have we have? We point 0.350 mole times 6.02 times 10 to the 23. Since we're dealing with molecules, it's going to be molecules, right, per mole, which then means mole cancels out. We end up with molecules. Okay. We end up with molecules, and that gives us 2.11 times 10 to the 23 molecules, right? Of what? Of C6H12O6, right? Molecules of C6H12O6. Right, now let's look at the next one. We got here, calculate the number of carbon atoms in 0.35 moles of C6H12O6, right? Of sucrose. Okay, now let's look at this. If we have, let's say we have say C6H12O6. Right, now as you can see here, if I write it like that, the coefficient in front of that is 1, right? So that 1 could refer to 1 molecule of it, or it could refer to 1 mole of it, right? So since we're dealing with moles, let's look at it and say, okay, if I have 1 mole of this, right? Because it's 1, we don't normally write 1, but I just want to illustrate the point. And we say, okay, 1 mole of C6H12O6 gives us 6 moles, right? Instead of saying off all the time, I'll say it gives us 6 moles of carbon, okay? And it gives us 12 moles of hydrogen, right? And it gives us, it has 6 moles of carbon. That's what this molecule is made up of, right? I mean this molecule, but if we represent it in terms of moles, so 1 mole of the substance has 6 moles of carbon, 12 moles of hydrogen, and 6 moles of oxygen. Okay. Right now, but we don't have that. We have 0.350 moles of C6H12O6. Correct? If I have 0. So how many moles of carbon do I have? It will be 0.35, right, times 6 moles of carbon. It will be 0.35, right? I just put it down to 2 decimal places. I'm not saying 0.350. So here, and then we have times 12 of hydrogen plus plus 0.35 times 6 moles of oxygen. Right, we are interested in this, and what does that give us? That gives us 0.35 times 6 is 2.1 mole of oxygen. Alright, now if we want N is equal to small n times the Avogadro's constant. So we want to know 0.35 moles of C6H12O6, how many carbon atoms does it have? So we first have to determine how many moles of carbon atoms it has, and we determine that, which is which is equal to 2.1, right, moles of carbon atoms times 6.02 times 10 to the 23 atoms, right, of carbon per mole, and that gives us 1.26 times 10 to the 24 carbon, right, carbon atoms. Okay, right, now let's look at the next one. It says how many oxygen atoms are there in 0.25 moles of calcium nitrate. Okay, if we have now, okay, one, got calcium nitrate, and if we have 1 mole of it, that's 1 mole of it, that means we would have 1 mole of carbon plus 2 moles of nitrogen, right, plus 6 moles of oxygen. Right, if I had, for instance, 2 moles of CaNO3, right, what would that mean? I would have 2 moles of carbon plus I would have 4 moles of nitrogen, and I would have 12 moles of oxygen, right? I multiply throughout by 2. But we have only 0.25 moles of CaNO3, right? So what does that give me? That would give me then 0.25 moles of carbon. It would give me, right, 2 times 2.5 moles of nitrogen, plus it would give me, I'll just do it here, 2.5, 2.5, 0.25, where's that? Let's just get rid of that. So this is not 0.25, it's 0.25, right? It's 0.25 times 0.25 plus that would give me 0.25 times 6 moles of oxygen, right? So, which would imply that I have 0.25 times 6 moles of oxygen, which would mean I have 1.5 moles of oxygen. Right, so now that I've established how many moles of oxygen we have, of oxygen atoms we have, we need to be careful, right? It's not oxygen molecules, oxygen atoms, and we want to know what is the amount of atoms. So N is equal to N times Na. So N is 1.5 moles, right? Times 6.02 times 10 to the 23 atoms of oxygen per mole. That cancels out, we balance with atoms, and that gives us 9.03 times 10 to the 23 atoms of oxygen. Right? Okay, so let's look at the next one. Here we have now an Avogadro's number. We have an Avogadro's number of cents, right? Cents. The South African cents. And this is divided equally among 250 million men, women, and children in Africa. How many rands would each have? Right? Same story. We say, all right, we've got now so many cents, right? We got the Avogadro's number of cents, and we know what the Avogadro's number is. So we say, okay, number of cents is Avogadro's number, right? Which is equal to 6.02 times 10 to the 23 cents, right? That's the amount of cents we have. Right, but how many people have we got here? Individuals, we could say it's 250 million, million times 10 to the 6, right? Individuals or people, or right, so we could say individuals, let's just say individuals, and that gives us then 2.41 times 10 to the 15 cents. Right. So many cents we have, but we want to know how many rands it is. So we say, okay, and in rands, okay, in rands, it would be equal to 2.41 times 10 to the 15, right? Cents. Okay, so it's cents, we can say cents, all upon 100 cents, and we know it's 100 cents per rand, isn't it so? which then means that is equal to 2.41 times 10 to the 13 rands per individual. Wow, per individual. That's a money for several lifetimes. Right. Okay, so we have that now. Let's look at the next one. Now we're looking at interconverting, right? We're going to interconvert between masses, moles, volumes, and a number of elementary entities, right? And you need to know this, okay? So let's look at it. Here you have mass. So we start off with the mole. Mole is the amount of substance here, right? And if we look at, we're relating it to the volume of the gas, we're relating it to the mass of the gas, and we're relating it to the number of particles. So we know that in terms of mass and molar mass, this is the formula. So that's what N is equal to here. N is also equal to volume upon molar volume, which we have dealt with. And N is also related to this here. Right, so if you have to convert between any of these, say if you are given volume and you want to know how many elementary particles, we could link these two formulas, for instance. Right, for instance, we could say here you got N is equal to V upon Vm. And here we have N is equal to a number of particles we got the number of particles over Na, right? So we know that that is equal to that, so which would imply that we have V upon Vm is equal to N upon Na. So you could use this, right? This is just an algebraic exercise in the sense that if we are now given the volume of the gas and the molar volume, we can find out how many elementary units we have, right? Right, so this is useful for you in a way so that you can then move from masses to moles to number of entities that you need if that is what you require. Right, now let's look at the next one. We have got here the amount of urea, right? Urea is a constituent of your urine, and we want to know the amount of urea in so many molecules. So in 2.3 times, we want to know the amount of urea molecules in that mass, which is used. This is actually used. Can you see that? It's actually used as a facial cream, and it's also used as an agricultural fertilizer. So what have you been given here? Here you've given mass, right? And you need to know the amount of urea. So we say, okay, M of OC NH2 right? We're getting its molar mass. And we say, okay, its molar mass is equal to 16, right? Plus 12, right? Plus nitrogen is 14, so it's 2 times 14. Plus hydrogen, there's 4 of it, so it's 4 times that, which then gives us 60 grams per 60 grams per 60 grams per mole. Right, so we got its molar mass. Right, but now we want to know the amount, right? The amount of urea. So we say N is equal to mass over molar mass of OC, right? N, let's do this properly. Right? OCNH2, 2, okay, and that is equal to 2.3 times 10 to the 5 kilograms, right? And to convert it to grams, I say times 10 to the 3. I convert that to grams, and that gives us, we know, 60 grams per 60 grams, 60, right, grams per mole, which is then equal to 3.8 times 3.8 times 10 to the 6 moles of what? Of right, of OC, okay, NH2, 2, right? That is the amount of moles of that. So it is so many moles of OCNH2, right? Of these molecules, right? Right, and if you want to know the exact amount of the molecules, then we just use Avogadro's number and we work that out. So here we got 3.86 moles of urea molecules. Right, now let's look at the next one. We got here convert each of the following masses to amounts, right? To amounts, moles, which is moles, to number of molecules. So we're going to convert it to number of molecules. But if they want atoms, then we will convert it to atoms. So convert each of the following masses to amount, right? To moles. And to molecules. But if we do need to, then we can convert it to atoms like it's indicated here. Right. So if you look at A, 1.80 gram of water, which would mean if I say N is equal to mass upon the molar mass of H2O, that would be 1.80, right? And we want to convert it to grams, so we multiply by 3. So that brings it to grams, right? And if we look at water, we know that water is 2 times the hydrogen plus 16, isn't it so? Right? Which would then be equal to 1.8 times 10 to the 3 divided by 18 grams per mole, right? And that is equal to, I'll just put it down here, and that is equal to 4.4 times 10 to the 3 moles. Right, 10 to the 3 moles of H2O molecules. Okay? So we have that, but it says we can then calculate the exact number of molecules, which we can say N is equal to N times Na, which is 4.4 times 10 to the 3 moles times 6.02 times 10 to the 23 molecules per mole, which is then equal to 2.6 times 10 to the 27 molecules of H2O. Right. Okay. Let's look at the next one. Here we have the number of phosphorus atoms in 100 grams of phosphorus, and the molecular formula of phosphorus, that is how it actually exists. It exists as P4, right? So if we want to look at this, which means M of P4 would be equal to 4 of it, and the mass of phosphorus is 31, which you can check in your periodic table, and that gives us 124 grams per mole, right? Per mole, right? Now N is equal to 100 grams all upon the molar mass of P4, which is then equal to 100 grams all upon 124 grams per mole, which is then equal to 0.81 moles. Right. It's 0.81 moles of P4, but how many moles of P do we have, right? So if we have, hence, we have 4 times 0.81 right, moles of P atoms, right? Because as you can see, this is asking for atoms, which is then equal to 3.24 moles of P atoms, right? But if you want to know in terms of the actual number of these elementary entities, then we say N is equal to N times the Avogadro's constant, which would mean 3.24 moles times 6.02 times 10 to the 23 atoms per mole, which is then equal to 1.95 times 10 to the 24 atoms of P. Right. Okay. So there you have that. Right. Okay, now let's go to the next one. It says determine the mass. It says determine the mass of one molecule of sodium hydrogen carbonate. And the next one says determine the mass of 1 mole of sodium hydrogen carbonate, right? Okay, so let's look at this. We want to know the mass of 1 molecule of sodium hydrogen carbonate, right? So if we want to know the mass of that, of 1 molecule, we go, and I said previously that we will just say, I'll write it like this in terms, if I write it like that with R in, then I'm getting the relative mass, which means of NaHCO3, right, which we know is equal to 23 for sodium plus hydrogen plus carbon is 12 plus 3 times 16 is oxygen, right, which is then equal to 84. 84, right, no units at all, right? But remember, when we wanted its molecular weight, then the molecular weight would be expressed in atomic mass units, which is 84 AMU, and that's for 1 molecule or 1 formula unit of sodium hydrogen carbonate. But we also know what the value of atomic mass unit is. Thus, we say, okay, it's 84, and the atomic mass unit is 1.66 times 10 to the minus 24 grams. So if we want its mass in grams, it will be then 1.39, not 1.39 times 10 to the minus 22 grams. So can you see the molecule's mass is extremely light, right? Then it says calculate the mass of 1 mole of NaHCO3. Or perhaps maybe let me just give you an alternative method for this. Right, let's have an alternative method. Alternative method Okay, you could do it like how I've done it there, or you can have an alternative method, right? And how do we have an alternative method for this? So we could say, okay, we know that N is equal to mass upon molar mass of NaHCO3, right? But we also know okay, but maybe I should just say instead of that also we have N is equal to N and is equal to N upon Na, which I showed you earlier, right? It's useful to use this. So here you got N is equal to that, and you got N is equal to this, right? And then if you got N, so which essentially means M upon M of NaHCO3 is equal to N upon Na. Right, which would mean now if we want the mass of a particular particle, which in this case would imply, right, M is equal to M of NaHCO3 times N, because N is the number of elementary units, so we want it of particle, and that needs to be divided by Na. Right, so we say, all right, we want a mass. So we know molar mass is 84 grams per mole. But what do we want? We want the mass of one molecule. So 1 molecule of it we want. Right? But that is 6.023 times 10 to the 23 molecules. Right? Molecules per mole. Right? And if we see if we look at this here like that, we could say mole cancels out with that mole, molecules with that, and we left with grams. So, and how many grams are we left with? We are left with 1.39 times 10 to the minus 22 grams. So that's an alternative way to get the same result. But if we look at the first one, and if you understand what you're doing conceptually, you didn't have to go through all this. Right, and the next one, it says here, what is a mass of 1 mole of the substance, right? So this is already there. If we know 1 mole of the substance, 1 mole of the substance would be equal to 84 grams, since we know, right, since M of NaHCO3 is a molar mass, so the mass of 1 mole of the substance is 84 grams, right? And the molar mass here is equal to 84 grams per mole, right? Okay. Now let's look at the next one. Calculate the moles of H2O molecules in a liter of water, right? And 1 liter of water has a mass of 1 kg, approximately a mass of 1 kg. Right, so we want to know the moles of H2O molecules in here, okay? So which means N is equal to mass upon the molar mass of H2O. But that is a kilogram, so it's about 1,000 grams. And the mass of H2O, which we worked out earlier, is equal to 2 times 1 plus 16, isn't it so? Gram per mole, which is then equal to that together, 2 plus the 16 is 18, which then gives us so this whole thing here is 18, so 1,000 upon 18, which gives us 55.5 moles of H2O molecules. Right, now it says determine the number of H2O molecules in 1 kilogram of water. Right, so that's A. B, if we want the number of molecules, so we just straightforward exercise, which is N times Na. We know how many moles we have, times 6.023. I'm saying 023 because we just take it to 6.02, right? Times 10 to the 23 molecules per mole. And how much does that give us? It gives us 3.34. 3.34 gives us 3.34 times 10 to the 25 molecules. Right? Can you believe that? It's like having a liter of water, right? You got a liter of water. There you got a liter of water, right? And this is a liter of water, and it's 1 liter. And how many molecules have you got there? Gee, look at the number, 3.34 times 10 to the 24 molecules in 1 liter of water. Right. Then it says, determine the mass of one molecule. Right? If we have to determine the mass of one molecule, then we say, okay, C, we want the mass of one molecule, so the mass of one molecule, right, we know it would then be equal to 18 AMUs. Right, if we're dealing with one molecule, and which is then equal to, I'll just bring my equal to sign this side, and which is equal to 18 AMU, which is then equal to 18, but we know an AMU is 1.66 times 10 to the minus 24 grams, which means that the mass of one molecule is 2.99 times 10 to the minus 23 grams. All right. Minus 23 grams. Right, so as you can see, it's like very, very light. Right, now it says how many hydrogen atoms are there in 1 liter of water. Okay, so we have D, how many hydrogen atoms are there in 1 liter of water. So we got 1 liter, right? And in 1 liter we know we got 55.5 moles of H2O. Right, if we have 55.5 moles of H2O, then how many hydrogen atoms do we have there? So it's 55.5 moles of H2O, which implies that I have got 2 times 55.5 moles of H in there. Isn't it so? Which means that I have 111 moles of hydrogen atoms in here. If I want to know now the number of molecules, so N is equal to N times Na. Right? Which is equal to so many moles of hydrogen times 6.02 times 10 to the 23. Now see, I want atoms of atoms per mole. Right? Hydrogen atoms. Here I ask how many hydrogen molecules there are, then we need H2 in there. At this point, we just want hydrogen atoms, right? Which is then equal to 6.68 times 10 to the 20. 6.68 times 10 to the 25 atoms of hydrogen. Right? Let's look at the next one. What is the mass of 0.5 mole of H2SO4? Right? What is the mass of 0.5 moles of H2SO4? Right, if you want to know that, which would mean okay, so we say N is equal to mass over the molar mass of H2SO4, correct? But what is the molar mass of H2SO4? we know that the mass of H2SO4 is equal to 2, right, times hydrogen plus sulfur is 32 plus 4 times 16, right, and that gives us 98 grams per mole. But we want to know the mass of 0,5. So here, getting there, we have mass is equal to N times the molar mass of H2SO4. Since we want to know of 0,5 moles times 98 grams per mole, right? And that gives us 49 grams. Okay, so that gives us 49 grams. Right, and it says the mole of oxygen atoms in 0,5 moles, right? The mole of oxygen atoms in 0,5 moles. Right, so how many oxygen atoms do we have here? If we look at H2SO4, so B, let's say A, and that's B, right? So you got 0,5 moles of H2SO4, which you can see if we had 1 mole, you would have 4 moles of oxygen atoms. Since you have 0,5, you then have moles of oxygen atoms is equal to 0.5 times 4, which gives you 2 moles of oxygen atoms. Right. Okay, let's go on to the next one. Determine the number of oxygen atoms in 4 moles of ferrous sulfate. Right. Sorry, that's not ferrous, that is ferri sulfate, right? It's iron 3 sulfate. If we look at this here now, and we say, okay, 4 moles of Fe2SO4 3. Right. How many moles of oxygen does it have? Right. So in terms of oxygen, if we look at determine the number of oxygen atoms in 4 moles of ferrous sulfate. So in 4 moles of ferrous sulfate, it is going to have 312. It's going to have how many? Determine the number of oxygen atoms in 4 moles of ferrous sulfate. All right. Okay, let's just maybe change this and let's change that. Instead of saying 4 moles, we will just change that and say let's change that to 1 mole, okay? Instead of 4 moles. So once we know the principle, we know what we're talking about. So let's change it to 1 mole, okay? To 1, not mole, so it becomes 1 mole of ferrous sulfate, okay? So that would have, that would then have 12 mole, right, of oxygen atoms. Right, because here you got 4 and times 3, which gives us 12 moles of oxygen atoms. If we want to know N, which means N times Na, right, and that would be equal to 12 moles times 6.02 times 10 to the 23 atoms per mole, and that would be equal to 7.23 times 10 to the 24 atoms. Right, so it could have been 4 moles of that. If it was 4 moles of the sample, then it would be 12 times 4 12s are 48. So then it would be 48 moles of oxygen atoms. So I'm just dealt with 1. Okay. And if we look at B, it says determine the number of all type of atoms in 1 mole of that substance. So if we want to determine of all types in 1 mole of that substance, then we're going to say, okay, if we look at Fe2SO4 like that, and let's break it up, that would give us say 2, right, moles of Fe, right, plus it's got 3 moles of S, plus it's got 12 moles of O. So total moles is then 12 plus 15, it's 17 moles. 17 moles of all types of atoms, right? In total, there are 17 moles of 17 moles, let's say, of all type of atoms. So then we want to know what's the number of particles. So we say, all right, N is equal to N times Na, which would mean 17 moles, times 6.02 times 10 to the 23, right, of all type of atoms, right? In total atoms per mole, and that gives us is equal to 1.02 times 10 to the 23 atoms of all types, right, per mole, right, atoms of all types per mole. Right, now let's look at this one. Calculate the number of molecules that will occupy the following volumes at STP. Right, we've dealt with STP, that's standard temperature and pressure, right? And that information is in your data sheet. gives you an indication what the standard temperature and what the standard pressure is, right? So standard temperature is 273 K and standard Kelvin, and standard pressure is 1 atmosphere or 1.01 times 10 to the 5 pascals, right? So if we want to know the molecules that will occupy 240 decimeter cubed of nitrogen decimeter cubed of nitrogen gas. So if we look at this here now, N is equal to volume over molar volume, right? And that is equal to 240 decimeter cubed, right, upon 22.4 decimeter cubed per mole. Right, that's the volume that it occupies. Okay? And per mole, sorry. And that is equal to 10.71 mole, right? So 10.71 moles of N2 gas. Right now, it's A. If you want to know the amount of molecules, so we say N is equal to N times Na, which is 10.71 moles times 6.02 times 10 to the 23 molecules per mole, which is then equal to 6.45 times 10 to the 24 molecules, right? 6.45 times 10 to the 24 molecules, right? Now let's see the next one. Here we need to know 347 cubic centimeters of CO2 gas, right? How many molecules we have there? So we first need to establish the number of moles, which is V, and the molar volume. I could do that, and that would give us, okay, that is equal to, okay, is equal to that's equal to it's equal to 347 cubic centimeters, but to bring it to decimeter cube we multiply by 10 to the minus 3 decimeter cubed, correct? If we're moving from centimeters to decimeter cube, we divide by 1000, and this is 22.4 decimeter cubed per mole, which is then equal to 0.0155 moles, right, of N2 molecules, okay, N2 molecules, right, of N2 molecules. Okay, we have that. But if we want to know the amount of molecules which is equal to N times Na, and that would be equal to 0.0155 moles times 6.02 times 10 to the 23 molecules per mole. Right, we know that cancels out, and that gives us 9.33 times 10 to the 21 molecules. 10 to the 21 molecules of N2. Sorry, not N2, we were dealing with O2. We were dealing with CO2. Man. That means we were dealing with CO2. So, sorry about that. That is CO2. Right. And here it is also CO2, right? Molecules of CO2. Let's just double check that. Yeah, right. Okay. So molecules of CO2. Right, that's correct. Okay, there you have it. And see you the next time.